Let me give you a brief description to the Rayleigh Taylor instability. You can check the details on section 4.7.1 on the physics of plasma. So the problem we're tackling with is basically the background condition. The background has we have background magnetic field on x and z direction. We have a gravity at the negative y direction going this way, and the displacement is a y and z direction, and we are taking a Fourier component of that. And we assume that the plasma is incompressible, so this is hold. So pretty much the problem can be demonstrated in this graph. Below the negative y, we have one homogeneous density, rho 2, and above that we have a rho 1. And the gravity is going this way. So if we to solve this problem, we need the first moment, or the momentum equation on y and z direction, and incompressibility. We have three equations, and one of the non-trivial step, at least for me, is the gravity. The force due to gravity is contributed by on the first order is the first order rho, the perturbed density, and the perturbed density can be expressed in this way. It's in a way Taylor expansion. So we have three equations. We can eliminate two quantities. So we eliminate Cz and P naught. So we left with this differential equation, and alpha y can be expressed in this way. It just make it look a little bit nicer. And for y not equal to 0, which is the boundary here, we know that the density is homogeneous. So rho prime is 0. Since for the problem we're tackling with, we assume that B is homogeneous with other boundaries. So this it becomes this. We're dealing with a little bit more simpler question. So alpha prime becomes 0 as well. So from this we left with alpha y Cy double prime minus k square alpha y Cy, and this is gone because this quantity is 0. So with an alpha y cancels out, then we have a wave equation. So we need a converge at infinity. So we're left with like exponential decay on both sides. Then to apply the boundary condition, we need to integrate from negative epsilon to positive epsilon, where epsilon is a small positive quantity. Basically, we're integrating a thin layer between those two densities around y equals 0. In other words. So we're pretty much integrating this. Prime is basically the derivative in terms of y, y direction. We know that this is a derivative and I integrated. Basically alpha Cy prime from positive epsilon to negative epsilon. Then we know that Cy prime we apply here. Then we have those two expressions. Alpha can be expressed here. It has two different densities at those two different locations, and we have this. For assuming we have magnetic field on both sides. Then we applied it to here. We ended up with this term. This term becomes this term, and all of those quantities doesn't vary. I mean it does vary, but doesn't vary dramatically. That means this term will be almost zero. This is alpha is basically alpha from negative epsilon to positive epsilon, but it's still small, so this is gone. And this similar principle, we have a prime, we have a derivative and integrate, then they become rho 1 minus rho 2, rho 1 minus rho 2. And to do some algebra, we will end up with this expression. So let's study 3 different cases. First, let's assume we don't have magnetic field. Then it become a pure hydrodynamic problem. So basically the expression without this term become this. Then we know that the stability criterion is omega star greater or equal to 0. Then we know that it is stable when the density below is higher, and it's unstable when the density below is lighter. In another word, you can think is like this is basically the wave, the water wave, because the rho 1 is air and rho 2 is water. And the unstable case, say you can think of like a hot coffee, and you pour cold cream in it, you can see those type of instabilities. Because the cold cream has a higher density, than hot water. Yes, you can see the mushroom thing. And when b not equal to 0, or just take this whole thing and we put the criterion greater omega square greater or equal to 0, and we know that if we take the theta as the angle between the k and b naught, then the k dot b naught become k b naught cosine theta. Then we have this criterion: k has to be like wave number has to be small enough number, or in other words, it has to be long enough wavelength, have long enough wavelength. And we study more relevant to fusion devices thing sometime. We have like something like we have plasma above but no magnetic field, and no like a vacuum, but we have magnetic field, and that's it, and gravity goes this way. So you can think it's like this is like a wall. So we have this expression. Basically, we do the same thing, but change the rho 2 equal to 0, and this term is gone, and this term survived. And then we're left, after some algebra, similar procedure, we're left with this expression. As you can see, the gravity here is destabilizing, and the magnetic field is basically in a way of pushing up the material of the plasma. It is a stabilizing term. Keep in mind the G might not be like a literal gravitational pull, but it could be due to other effect, say curvature, like basically magnetic tension. Yes, so this is destabilizing and this is stabilizing. So if we have a big enough magnetic field, then they can hold the plasma.